Okay, so hello, welcome everybody. Welcome back to our whole training sessions. Today, I'm very happy to introduce Dr. Shirui, who is a research scientist at NCSA, and Shirui is going to give a tutorial on how to use PyTorch. Oh, actually, I'm sorry, TensorFlow. Tutorial on TensorFlow. We will have a PyTorch tutorial next week. So Shirui, please take it from here.
Okay, all right. Hello, everyone. Welcome to this workshop. All right, so today I'm going to show you some of the basics of how to run a TensorFlow models on our cluster HAL. So first, if you are first-time user on HAL cluster, this is let me get my. This is a wiki page. Oh, actually, I have a Google Docs show you how to get started on this cluster. If you never use it, you need to create an account on HAL. Yeah, the link of this Google Doc is in the chat. Right. And let me know if you cannot access to this Google Doc. But if you do already have accounts and you have used HAL before, then you can go to this link. It's HAL on demand, because today all the demonstration will be on Jupyter notebooks. So this will help you to open a Jupyter notebooks on HAL. So maybe I can show you what it looks like now. So at this front page, you can click on interactive and do Jupyter notebooks. We do have a specific reservation for this workshop. So if you put this into this normal reservation and say we have 2 hours for this training, we're going to use GPU, so 1 GPU and CPUs, and you can launch it. Show you how to get rid of this. Yeah, it can be a little slow for now. If that's a lot of people try to initiate a Jupyter notebook at the same time, then we're getting there. Okay, so click connect to Jupyter notebooks. Once you already into this, you also have to open a terminal, because our training materials is in my GitHub. So if you can open a terminal and get clone this repo.
You mean terminal on HAL system, so that needs to be on HAL.
Oh yeah. So I can also show you what to do. So assuming here is your local terminal, and you can do SSH, your username, HAL login to NCSA Illinois edu. Yeah, we ask for your password. And the dosing. And yeah, just make a folder like HAL training or HAL training, and go to this HAL training and do the git clone. All right, so yeah, you will see a folder called hot training, and all our training materials will be under this folder. Yeah, so let us know if you have problem doing what I just showed, like in accessing to the cluster, or you have problem copy this repo. See questions here. I'll give a few, maybe 20 seconds to allow everyone to copy this repo.
Now, if you do not have an account on HAL, you can actually copy this repo to your own laptop or your own computer and run the notebooks from there. But that's kind of your your own setup.
Okay. Yeah, I don't see any questions. Oh, that's so I just started. So we'll start with this Jupyter notebooks. It's called Intro Keras 1. Okay, so the goal of this tutorial or this whole workshop is really to help beginners of TensorFlow users to have entry-level understanding of the basic components of TensorFlow. It's better if you have a prerequisites of Python, NumPy, machine learning, neural networks, just some intro-level understanding. It would be very helpful. And also a claim is some of these tutorials I use this open source GitHub repo to prepare this this workshop as a reference. Yeah, so we're gonna start with so the steps in modeling with TensorFlow. So the step 0, the very beginning, you need to get your training data ready. It can be a table data in CSV, or if you do computer vision, you got images, and you kind of have to prepare it to be some data formats that TensorFlow can work with. So TensorFlow can work with NumPy, and also it can work with generators. So which we will cover later. But at a very simple example to begin with, we're gonna stay with NumPy. So for example, if you have a CSV file, you're gonna read NumPy, read into NumPy, and we'll start from here. And then the next step will be you create a model by defining the inputs, outputs layers, and hidden layers of, for example, for very simple neural networks, which is a feed-forward neural networks, you can have inputs layers, outputs layers, and hidden layers. You can have multiple hidden layers, and each hidden layers you can have multiple nodes. So all the details of the architectures will be well defined in this step. So we're going to show you how to do this. And then once the architecture is defined, you need to give the details of the compile. compile with loss functions and optimizers and evaluation metrics. So the loss functions really kind of measure how bad your model is or how good your model is by measure the kind of the dissimilarity between your model outputs and the true result. So this is something we really want to minimize during the training session. And optimizers, we will show you a couple of examples of popular optimizers in TensorFlow. It's just different ways of how you can optimize to achieve the minimum loss function. And finally, it's evaluation metrics. It's how you interpret your model performance. And then step 3 is usually once the model is well defined, you can fit the model with your training data. So allowing the model to find the patterns between features and labels. And then step 4 is after you feeding the model, most of the time you need to fine tune the model by doing multiple experiments. Sometimes people call it hyperparameter tuning, which means you may not have an optimal model architecture. You may need to have additional hidden layers, or you have too much hidden layers. So this overfeeding, underfeeding issue you will have. And sometimes you need to change to different loss functions or optimizers, or even learning rates. So all these hyperparameters, you have to kind of iteratively go through this create a model and feeding a model many times before you find a very satisfying model. And the final step is to visualize and interpret the results and save your trained model for later usage. Okay, so with this frame, I first start with to create very easy data for us to use. So the first thing we need always to import the required packages. So we're going to use NumPy and TensorFlow here. This is something if I don't know if the whole node sometimes is very busy, and it seems we can have especially on Wednesdays when there's class and training sessions, a lot of people will use whole computing loads. So somehow I need to use this to enable memories for my usage. But most of the time, you don't need to worry about this. So now this is an easy data set I create. I first set up the seeds. So just for reproducibility. Then I have X data, which is a NumPy array ranging from 0 to 20. And then I have Y to be 2 times X with some noise. So the noise is just a random term. And then once this X and Y NumPy array is created, I convert this NumPy array into TensorFlow tensors using this function. It's called TensorFlow constants. And here, we can try to plot and see how it looks like using this matplot library and do a scatter plot. And let me run this. And this is how our data looks like. You see the X ranging from 0 to 20, with Y 2 times X. So roughly it's ranging from 0 to 40, with some fluctuation because of the noise term. So we try to mapping a regression between Y and X by using TensorFlow. So so once the data is ready, then we can work on model creation. Here I use the TensorFlow Keras sequential APIs. So this is a high-level API. It's very intuitive to start with. So sequential is really self-explanatory, meaning your models has to be like layer after layer after layer, linearly. We're patching layers, all layers sequentially together. So in this case, I only give a one single layer with node number 1. So it's the simplest neural network model. So this is our model architectures. And then the next step will be for the model in this compile, we need to give 3 things: the loss functions. This is also from Keras API. You can have mean absolute error to be the loss functions. And there are quite a few loss functions we can choose. For regression, most popular ones is like MSE, the mean absolute value, or mean squared error. But we're gonna use mean absolute error to start with. And optimizers, here I use Atom. But again, you can use many other optimizers as well. Like stochastic gradient descent. It will be something like SDG, something like this. You can replace Atom with other optimizer as well. And metrics, here we also use mean absolute error. So once the compile is also well defined, we can start fitting the model by the X and Y, the training data. And we define our epochs. And you can see it start running. So the outputs have our loss functions after each epochs, and our metrics here we define to be the mean absolute errors. Remember, we are try to do a regression between Y and X, which is really Y to be 2 times the X. So you can see how the MAE is kind of decreasing during the training. And once the model is built, you can do a model summary. This is really to help you to see the details of your neural network architecture. So you have a dense layer, which is the parameters. We only have 2 parameters. So that because if you remember how we create the model, really it's just 1 layer. So the 2 parameters are just the W and the B. The W, which is the weights and the bias in a single layer of neural networks. So that's the model summary looks like. And then you can so the model has been trained. So now you can do some inference, assuming you are interested to know for the model, if I have inputs x equal to 10, what the model gives you. Okay, some number close to 20, right? We know we have some random terms, so it's not too bad, right? The model give us a reasonable value in this case. So yeah, this is really the a simplification of how you can build a TensorFlow keras model. We're gonna gradually adding the complexity to the model in the next tutorials. But now, so in our last example, we have really the simplest neural network. So what if we want to, we are tackling a more complex problem, and assuming this simplest model will not work very well, then you have to kind of increase the complexity of the neural networks by adding more layers, and also increase the number of hidden units. Sometimes you need to change the activation functions depending on regression problems or classification problems, and also different optimizers. So here I give an example of using keras sequential to build a more complex models. So in this time, instead of just one layer, we building multiple layers. So 1, 2, 3, 4, each layers. So the first arguments here, it's the number of nodes in this layer. And then you have this activation function. It can be ReLU or sigmoid. There are many options you can find. So this is a more complex models. Here we don't change the compile informations here, but again, you can also tune it into different ones, test it with different ones, and see how the model performs. Let's run it. Okay. You can see the model summaries. It has more layers. Similarly, you have model predictions. We can also visualize our models. So what we do here is we give all the X which we used for training into prediction, and this will give us a list of predictions. And we're gonna plot the true data against the predictions ones. And you can see the model is doing quite well. But here I just show you how to build two models in keras very easily. And also in practice, a typical workflow when building neural networks, usually it's like you build a model and you fit it, and then you evaluate it, and you're less satisfied with the model performance, so you have to tweak the model a little bit, and you fit and evaluate again, and tweak the model again, and until you find a satisfying results. Okay. I see some message here.
Yeah, and I think we sorted out one of the login errors already.
Okay.
And I'm chasing another login error. So
How many participants having this issue? It's everyone or just?
Sounds like only 2 users, but they are new users, so they haven't used the system before. So that.
Oh, okay.
I
So
think you can continue this tutorial, and I will kind of work in the background to sort this out.
okay, yeah. So yeah, you can stop me or put your question in the chat if you have any questions about the tutorials. And so also like a very good learning website, it's the TensorFlow official website. So for example, if you are interested to know like what are the loss functions available, you can see that's quite a few. We use mean absolute errors, but there are many ways you can choose from, and same as for the matrix and the optimizer. Yeah, that's for tutorial 1. If you have questions, let me know. Okay, so Yash, he has a question about number of nodes in each layer do. So the number of nodes, if you look at neural networks, yeah, you can see, for example, in this hidden layer, you can have multiple nodes for each hidden layer, depending on how the non-linearity of your problems. Usually, if you add more hidden layers, your neural networks is more capable to mapping a non-linearity problems. So that's what I mean, the number of nodes in each neural network, in each layer of neural networks. So yeah, also the training is about the usage of TensorFlow. So if you have questions about like in general neural networks, I think there's quite a lot of good materials you can learn online. Okay. So I work on a second one. So I'm splitting this workshop into multiple Jupyter notebooks. Just sometimes I feel like it's kind of easy to get lost in Jupyter notebooks if the Jupyter notebook is too long. So let's open the second one. Okay. So for the first tutorial, I show you the whole steps to modeling in TensorFlow. In these tutorials, we're gonna cover some basics on how should we split the data into different like training, validation, and testing. Because in any machine learning or deep learning models, when you train your first model, ideally the data in testing should not be seen or should not be used when you do the training. So assuming you collect a lot of data in your lab, you want to build a model, then the first thing is to try to split the data sets into 3 different data sets. Usually we do 70, 15, 15. Here also I give an example similarly to how we create the data sets. We create a NumPy array ranging from 0 to 100. And similarly, the y is to 2 times x. Let me run this. And here how is the data looks like, just 1D x and 1D in y. And then you can use a package in sklearn to import a train test split. So this methods can help you to split your data into training and here I call it remaining. But what really it does here, it's just the percentage you want to keep in your training size. If I do this, if I look the size of my training and testing data or remaining data, you can see originally I have 100 in the data size, but now we have like 70 and 30. And then you have to do it again for splitting the remaining data into validation data and testing data. So for this case, we want to 50-50 split. So what we do is we're splitting this 30 into 2 50s. Okay, and once your data is splitted, so again, here's the piece of code I copied from our the first tutorial. I won't just copy here for comparison because now the difference is when you build a model, you can actually give names for each layers. This is just better for visualization in the following. Otherwise, it's easier to get lost, like which layers is what. So you can do something like this. Also, in the first layer, you can give the input shape. This argument is really used to assuming your data X has multiple features. For example, it has 5 or 6 features. Then this input shape should match to what the shape of your input. We can run it now. And now you can see we give a name for the model to be a simple multiple layer perception model for our whole workshop. And this is the layer name. If you have 2 layers for your neural networks, you can see 2 layers with their names here. Okay, you can also train the model. Yeah, this is something I found. A solution to this is what I just showed. Okay, let's rerun this. All right. Okay, it is running. So here I give 4 approaches. But if you do robots equal to 0, that means you will not see this long list of outputs, just for clean purpose. Let's see if it's finished. Okay, it is finished. Now the model is trained. Let's do prediction. So now instead of predict on the training data, we predict on the test data. We just split it. And if we plot the training data and the test data and the comparison, the tested the true label, the true outputs with predicted outputs, and you can see kind of visualize the performance of how your model is when you do this regression. Maybe if I comment this layer, so okay, this label should be test test true data test predicted. So yeah, it's a visualization how your model performed. And then in TensorFlow, it also provides some metrics to evaluate the model performance. There are MAEs and MSEs. You can call it separately. If you do NumPy, this gives you how the mean absolute error of the tested and the predicted values. Similarly, for MSE, the mean squared error, you can do things like this. So once the model is trained and you kind of visualize and you see the model is doing quite well, and you have metrics to also agree that the model is doing wonderful, then you can save your model. So the model, you can save your model for later inference use, or you can save it so you can share with others of your model. The TensorFlow has 2 ways of saved your model. So what you do is you can just give your model saved pass, and then do the model.save. Or you can save it using the HTF5 formats by changing your model path into something like this. I see someone raise hands. Yeah.
I have a question about, like, when you save model, do you save like trained model or just like the architecture of the model?
Actually, the architectures and the weights and the bias that you fitted will both be saved.
So like you save the like already trained model, right?
Yes. So
Okay.
for example, later when you want to use your model, you do not need any training data. You do not need to redefine your model architectures. You can just easily, like, this is something I can show you very quickly. So assuming you do this save the model by calling these functions, and the model is well saved. So when next time when you or your collaborators when they want to use this saved model, they just need to do a model load by load the model and give it to different names, and we can actually see it, and you can use it by just doing prediction. So this way, you don't need to redo any training, or you do not even need the training data anymore. Is that answer your question? Does this?
Yes, yes, thank you.
Yeah. Okay, so also for TensorFlow, not only it can save a finalized model, it can also save some intermediate steps. Assuming you have a very big model, it takes, I don't know, it takes maybe a week to finish. But you don't want to wait for a week to save your model, right? Maybe something happened and your model is stopped, and all the data you will be lost. So in TensorFlow, even like you haven't finished the training, you can still save some of the training, like the weights and bias, this hyperparameters, by this training checkpoints. So you can easily follow this because of the time limitation. I'm not show you how to do this, but there are you can, okay, it's in Chinese, sorry. How you can, yeah, if you click this, you will see this in English, I believe. But yes, this is something also doable. You can save the intermediate results, not only just the final model. So is there any questions for this tutorial? If no, I continue on the third ones. So in this tutorial, I want to show you how you can use TensorFlow to work on a real data problem. So I know a lot of you, a lot of our users on how they have data like stored in a CSV, and so I just want to give an example of how you can use this to build your model. So here I use insurance data. This data is publicly available. It's called medical cost personal data sets. So the data is in CSVs, and the data have multiple columns, like age, sex, and BMIs, and children, smoker, etc. And finally, it's the insurance charges. So what we want to do is, given like the age, sex, BMI, children, all these features, we want to build a model to predict the charges. So if you look at the data, so the charges is a continuous variables, which usually requires little sense to pre-processing. But for regimes, this is categorical data. So you have like southwestern, southeastern, maybe northwestern. So this kind of data, it's not readable for TensorFlows, right? TensorFlows is really, it can do math operations on integers or floats, but not like something like southwestern or northwestern. So you have to convert this column into something that TensorFlow can understand, and also for smoke as well, and sex as well. So one way of doing this is we call dummy variables. or there are like one hot encoder, this type of thing. If you don't understand what dummy variables or one hot encoder is, you can easily find this online, and basically it's try to assuming you have like female and male, then if you do one hot encoding, for female you have values like 0, 1, but for male it has values like 1, 0. So that's just the way how you can differentiate female with male using like integers or float instead of this categorical variables. So okay, so we're gonna do this. We're gonna first, this is something we just covered. We're gonna split the training data. We're gonna split the whole data into training and testing. Here, just for easy demonstration, I don't include the validation, but you can do it yourself. For X, we drop the charges from the whole insurance data set because that's what we want to predict, right? For Y, we just use the charges. And you can split the data. If you do this, you can see roughly we have 1,000 for our training, and we have 6 features. So 1, 2, 3, 4, 5, 6. And that's our training data looks like, and that's our testing data looks like. Okay, this is some pre-processing which I just mentioned for to work with data that are categorical. So we have 3 categories of data: sex, smoker, and regime. So what we want to do is we want to use this method called one hot encoder to pre-process it. And for the other 3 continuous variable, we're going to use what we call min-max scalar. So this is really try to like normalize the data so it can range from 0 to 1. So after we're doing this, also we have a mag column transformer. This is really to kind of create a pipeline to link all the pre-processing method together. And once you do this, we name the pipeline to be CT, and we can feed our train data, and then after we feed it, we can transform the train and test into what I call normal. And also it is worth noted that when you do this fit, you do not put all the data to fit, because when you fit it, it's like you're fitting a model. You really don't want the test data to be part of your fitting, but you can use it for transform, right? So I guess I can show what the test train normal. Can we do view? Yeah, so this is how it looks like. If I want to see what my previous before pre-processing, this is how it looks like. Oh, I do not have X train. Oh, it's capital X. Well, is this because my train it's what is this? Okay, it's a data frame, so we need to use something like Yeah, this is our data before pre-processing looks like. It has 6 features, but once you're done with the min-max scalar and the 1 HAL encoder, you will have something like this. So I guess if you do hat, that's better maybe. Okay, this is not. Yeah, this is a once it's transformed, it become a lumpy array. But for example, this samples will be transformed to something like this. Okay. So once your data is well ready, you can start building your neural networks. Here I just gave an example using 3 layers. Each layers have this number of nodes. The inputs here to be noticed is that this has to match to your shape of your inputs. So if you do shape, you can see now your training data has 11 features. So this is just number of samples you have. So the numbers here has to match the numbers here. All right, so we create a model, which is again similar to the previous 2 tutorials. It's also a feed-forward neural networks with just 3 layers. And we have this compile information, the same as last 2 tutorials. Here we add another thing, which is called callback in the early stopping. The reason is I can demonstrate it later. The reason is that if you do training, so the approaches is really how many iterations you want to run for the whole data set. Suppose you do not have this callback. Let's comment this off. Well, what's the error message? Good at runtime. Okay, out of memory. I have to rerun it. Good at runtime. Should I initialize this stupid notebooks? Let me try reopen this stupid notebooks. It says our CUDA is one of the GPU is out of memory.
Yeah, so it looks like
Too many.
yeah, that's an issue with the notebooks that the GPU memory never gets freed.
I guess I could just reinitiate a session. Is that the solution?
Yeah. So I think you have to, because this notebook is always running there. So
Let's delete it.
yeah, if you delete it, rerun it or something like that, that might help. There is a trick somewhere there, what you need to do to release the memory. TensorFlow has this, in features that it keeps adding memory, but it never releases it until you exit.
Yeah. Someone posed this question. Yeah, this is what I just saw. I can show you a solution how you can do this. Once I go back to this. This is also related to the memory thing. Do you have a elegant solution to this, Vlad? This is something which I can show you. So it seems like if I have a lot of qubit notebooks running, then sometimes the memory is kind of out of memory, and then I will see this kind of error. But one solution to this is let me do this.
Yeah, I think there was solutions that were posted in the support channel at some point, but
yeah, so this is what I do. It seems like if you enable this physical device to have memory groups enabled, then the runtime initialization will not allocate all the memories on the device. So if you have this two, 3 lines, you will get this issue solved. Yeah, let us know if you still see this after trying what I just showed. Okay, so let's go back to this time I can run them all. Oh yeah, it says callbacks are not defined, so that's easy fix. So yeah, let's getting back to where we left. So this is we're training, we're feeding the model, and so it's getting done pretty quickly. You can see the training process by so here's a plot you can actually use. So this is how your loss is decreasing when you're training with the epochs. So the epoch is also it's something like user defined. Sometimes you don't know how many epochs you can run. For our case, it's a really simple and small neural network architecture, so you can just try it. But usually, when it's a large one, you don't want to just shoot a blindly a number here. So because otherwise you will have a lot of vast resources, computational resources. You can see like after maybe 25 epochs, the loss function is really not decreasing that much. So which means your training can be stopped around 25. So with this callback, so TensorFlow has a very it's a very functional function. It's called early stop. So it will detect like if the loss is not decreasing that much, then it will stop ahead. Even you say 200 epochs, it will stop even at 25. So let's see we add this back, this callback function, and you can see, early stop. Okay. So yeah, so the model decide instead of 200 at 52, it seems the model will say we already achieve a plateau, and it's pointless if you keep do the model feeding. So we'll stop early, and then the model is trained, we can use predict to predict the results, which is the X test. And you can also see so the model performance by looking at the mean absolute errors. So we can check how our model performed. So if you do Y train, which is our maybe Y test, you can see the insurance, the mean charges for insurance, it's about 12,000. But you have a mean absolute error of 3,000. So the model is doing relatively okay. It's not like exciting, but that can be different. It can be related to hyperparameter tuning, or your numbers of training data. It's not that huge. We only have 1,000 lines. And here's the plot. After we're using the early stop, you can see instead of 200, the model stopped earlier. So yeah, so this is what I want to cover for this tutorial. So any questions so far for this? Okay, if no, yeah, so we're gonna work on the next one. In last tutorial, I showed example using TensorFlow for regression problem. Here I want to show how to work on a classification problem. So everything is pretty similar. Just you have to be careful for a few things. One thing is like, because classification, you essentially you want a like 0, 1 thing instead of continuous variables. So maybe the last layer of your neural networks, you have some special treatment. So if you are expecting 0 and 1s and you get a 1,000 or 2,000, that does not make sense. So which means we just need to add actual activation functions in the last layer. We'll do our things for importing all the required packages. And the data, it's not a realist data. We're gonna use a method in sklearn. It's called Mac circles. You will see how this method can, what data this method can generate. So we want to generate 1,000 data points. So by calling this Mac circles and just give some parameters for this Mac circles, and this will return two lumpy array. We're gonna plot how this lumpy array looks like. So for the X, it has two columns. For the Y, it's really just the indicator. So if I do this, you can see this is how it looks like. So X has values. So the values is really like first column is the X coordinates, and the Y column is the next column is the Y coordinate. And we're doing a scatter plot. The color is indicated by Y. So Y will be a lot of 0 and 1s. So if it's 0, it's one color. If it's 1, it's another color. So that's how our data looks like. What we want to do is we want to build a model classifier, so we can classify for every point. We can classify which category it belongs to, right? So if I do this, maybe I can show you the raw data looks like. If you do circle head 5, so this is our data looks like. So which we just mentioned, x0 and x1s are the coordinates in x and y axis, and y, which is a label, it's indicators which group it belongs to. So we have 1 and the zeros. Okay, so now we have the data. We're gonna start creating the models. So there's nothing particularly different except that in the last layer, we're using activation functions. The reason is because, we're using sigmoid to be the activation function because if you never know what sigmoid looks like, here how it looks like. So for different kind of inputs, the sigmoid can work. The inputs of sigmoid can be from negative infinity to positive infinity, but the outputs will always be in the range between 0 and 1. So that's a sigmoid function looks like. And this is a perfect function you can use. We can think about to use for classification, right? Because essentially our model outputs, we want to be a value either 1 or 0. If we, by default, if we set the cutoff or the threshold to be 0.5, then any outputs below 0.5, we can classify it to be 0. Any outputs above or in the range between 0.5 and 1, we can classify it to be 1. So that's pretty intuitive. And another difference that in the loss function, previously we used MSE, the mean square error or mean absolute errors. But in classification problems, there are better options. Here we call it binary cross entrophies. This is if you have two binary classification problem, this is better to use. Optimizer, we use the same thing. We also adopt early stopping here, accuracy, everything. So let's run it and see. Okay, do we see the same issue? Cool. Oh, again. Yeah, seems I need to figure out how to free the memories after I run Jupyter notebooks, but I'm gonna restart again. Does any of you encounter this issue, or any of our audience have the same issue or not? Oh, you do? Okay. I'll figure this out maybe later and post it somewhere in our HAL wiki page, like how to work this out. But sorry about this. Yeah, I try to rerun and see if I have the same issue. Oh yeah, I have to restart my All right. Okay, I just rerun everything. And here just the function to plot the decision boundaries. I don't want to cover this, but you may figure out this later. And you can see the model is doing pretty well for classifying by looking at the bounding conditions, right? The white plot really differentiate the two categories pretty well. And here's just the plot of the loss functions and your evaluation metrics, which is accuracy, looks like. So that's how you can. That's an example of how you can do classification. Okay. So any questions for this tutorial? Next one is about data generator and the data augmentation. So why I have this to be a separate tutorial, because when I first work with TensorFlow, a lot of times I'm building from somewhere else. Either it's a open source package from GitHub or somewhere that publicly accessible. A lot of time, it's not the model that's so the model has already been taken care of. A lot of times, it's your data, because you can easily find your data is different than their data in terms of formats. Either they are using or they're using a data that's have different shapes. For example, NumPy, someone has a 4-dimensional NumPy array, but you only have images, or etc., etc. So getting the data correct and fitting the data into a model, it's kind of sometimes can be tricky. So so in this tutorial, I'm going to show you how you can use. So instead of just a NumPy, like how can you use TensorFlow the data sets to build your Python generators, and even better, you can enable augmentation. And another reason for I'm introducing generator, because I know some of our users on HAL, they have really big data sets. So it's impossible to kind of load all the data sets as NumPy at the same time, because you will have this run out of RAM problems. So you really have to use a generator to kind of undergo reading the data in a batch mode. Okay, so I'm gonna import the data from a Keras data set. It's called fashion MNIST. So MNIST is just a digital number data set. Fashion, it's like some of the data are just like clothes, like T-shirt or anything. If you do this load data, you will have two tuples. So that gives you X train, Y train, X test, Y test. So I'm doing this. You can see that the data for training, and it's the data type is integer with 16,000 images. Each image is 28 times 28 pixels. And we can check the data size. it's not too big. Even we load it into NumPy, it's only 0.05, around 0.05 gigabytes. But you can think of like the tip. Here's a plot of how it looks like. So I can randomly having an index, which gives different images from the trained data and plot it. Like this is a shoes. This looks like a shoes. I think if you do differences. So yeah, this is how data looks like. It's all fashion things. So remember, the data type is integers, right? So, but TensorFlow works on a lot of like multiplications and activation functions. Essentially, your data will be like a float. And also a common practice that we rescale the data into by divided by 255. If we do this, all the integers will be floats. And also the images, usually they have 3 channels. So the images we have now, it's only 1 channel, but sometimes you have 3D images in RGB channel. So that makes your images like 28 times 28 times 3. Or if you have a high resolution image, it's like 128 times 128 times 3. But I just want to do and to show you, if we do this kind of pre-processing and adding 1 dimension, then your data will be like for 60,000 data, the data size is like 0.37 gigabytes. And if you have 100 times small data up to 6 million images, then your memory can be roughly like 37, which can be too big. So it's almost impossible, or at least less memory efficient, if we try to load everything at the same time. So what are the solutions? Well, the common practice is you load your data in a batch mode. So instead of all of them at the same time, you just do batches like 32 or 64 at a time, and so read it sequentially. Then what are the tools that can help us to do this? This data set dot from Tensor slides is really helpful. So the data set in tf.data, it's a Python iterables, which similar to like a list. It's produce a sequential elements. If I create a data set by doing tf.dataset from Tensor slice. So this, I give you a list with 4 elements, and I can do a for loop to kind of print out this elements in data sets 1 by 1. So also you can do iterate, and if you do this, and if you do next, so you can see if I keep this, it goes through 1 by 1 until its end. It's ended, so that's why you see this error. Okay, so so I just show you how can we use the Tensor from Tensor slides. Now let's try to reload the data again. Let's reload it, and this is data which I just show you previously. We just do a reload and rescale by 2 255, and we do the same thing for test. And so once we get in the data, you can call this from tensor slides method in tf-data.datasets for a tuple pair of imagery and labels. And this will create you a batch dataset. And then we specify the shuffle size to be 5,000. This shuffle will help you. So instead of just orderly getting the training data, sometimes you want to shuffle it. So just to involve more randomness to your training data, this can be helpful sometimes. And the batch really means instead of loading every data, all the data, we do in a batch way, like so each time only 32. And this is the same thing we do for prediction for testing data. So we just do, so this image and label is from the training data. We also do similar thing for testing data. So now we have 2 batch data sets. Okay, I need to rerun this. We can have a pic of how the batch data looks like. So I have an iterator for this. If you do next, so that would be the next batch of the data, how it looks like. So remember I do 32. So the data now has a shape of 32 images. Each image is 28 times 28. So that's how the images looks like. And you also have labels. If I go to the bottom, and this is the labels looks like. It's a 32 array. So by doing this, using this, you can have a generator that feed your data in a batch mode. So now this is similar. We're building a model using CAII sequential. We just run it, and we feeding the batch data into our model by doing model fit. Oh, what errors message I see? Okay, this is a similar thing we saw before. I guess I just need to copy the files. And paste this somewhere at the beginning, and then rerun everything. Okay, it works now. Well, yeah. So you can also use a repeat method after a batch data sets. So this way, it's like an infinite data set. If you don't specify this 2 parameters, it will not finish. It will keep running forever. But doing this, you can say we only run 6 epochs. Each epochs with just the steps updating 40 times. So once this is done, then your model will stop feeding. And once we are done with training, we can do this prediction. The prediction will also require you to do the same thing for your test data set by create a batch data set using this from Tensor slice method. And then you can do model prediction. Here's the size of your model outputs. So it's really the batch size times the steps. So this is what I just showed you is how to use generators to train a NumPy data in a batch mode. So so what if your data is too big to fit in at the same time, right? So this method is still assuming you have a single NumPy input data. If your data it's in your folders, right? Your folders you have many images or videos in the folders. Then what you should do? So this data generators they have methods to treat this. So I can open this. So if you were here last week with us in our tutorials, the last Wednesday, for the same time for this workshop, then you will learn like in our last workshop, we show you examples of how to create a generator by just reading data from files. So here's, for example, here's here's a GitHub link. You can follow this and to learn how to do the data generator by reading from files. Yeah, maybe we can quickly go through this. So this is downloading data from a web link, and you unzip it, and you will have folders for CAII 10 data. And these images will be like PNGs or JPGs files under this test and train subfolders. And then you can use image data generators to create this generator. And like here, you just using the image data generator, use methods called flow from directories. So specify the directories of your where your data sits and target size. This will help you to resize the data. If you data is 128 times 128, it will do resizing by some like nearest neighbor method or whatever. But essentially, the image will be resized to be this target size. And similarly, batch. And you're creating generators for both training and validation, which is actually testing. And you can feed your data using this generator. So yeah, so this yeah, maybe some of you have attended this session last week, so which will be helpful. But if you did not come last week, I have the link for this GitHub you can easily follow with. So let me see. Any questions from our audience for this tutorial? Okay. This is, let me see. What time is now? Okay, we still have about half an hour. For the last 5 tutorials, what we covered is really using this high-level Keras API to build models and fitting out models and visualizing, some fine-tuning. So from here, we'll work on some TensorFlow directly instead of using Keras API. So why we're doing this? Because sometimes so Keras is really handy for you to build your first models, and it can work very well for most of the problem set you have. It's very powerful. It has all these functions available for time series data or language models or computer vision models. But sometimes if you do really scientific work, which means you may try to be innovative, and you want come up with something that Keras has never been have never defined before, then you need to use TensorFlow basics to help you building your models. So that's why I want to include this in this tutorial as well. We can quickly go through this. So I'll start with TensorFlow basics. So the two data units we're going to cover, it's called tensor and variables. So in TensorFlow, the tensors are very similar to NumPy arrays. They are multidimensional with uniform data type. You cannot have mixed data type in tensors. Unlike NumPy array, they are immutable. You cannot, once it's created, you cannot reassign a value to any of the elements inside the tensor. And also, tensor is designed for running more efficiently on GPUs rather than NumPy. NumPy is really not designed for CPU use only. There are packages where you can wrap your NumPy and running this on GPU, but by default, it's not designed for GPU or TPU usage. Another thing we call the variables. So this contains a tensor, but the good thing is that they are mutable. So if you have neural network architectures, or let's say in linear regressions, so y equal to w times x plus b. So x and y is your training data. They do not need to be mutable. They are like constant. So that's why mostly they are tensors. But this parameters, w, this coefficient, and this intercept, they are something that you need to iteratively update it during the training. So they have to be immutable. They have to be mutable. That's why most they are variables. So we're gonna show you how to do this. So you can easily create a tensor by call this tf constant function, and then if you have a 2D list, then this can be used to convert the 2D list into a tensor. So if you do this, what wrong? Oh, out of memory again. Okay. Again, let me know if you have questions, or you can, if you have very specific questions about your, you can solve it by shut down previous notebooks, which I did. Every time I finish my tutorial, I close it. Okay. So that's my training right here. Okay. Here we go. All right, so this is where we left. You can see a tensor is created with shape 2 times 2. So this is very similar to NumPy, actually. You have 3 characteristics: the data type, the shape, and number of dimensions. So shape is 2 by 2, and number of dimensions is 2, since it's 2D tensor. Okay, there's other ways you can initialize, or you can create a tensor, like zeros. We create our zero tensors. These are also similar to NumPy. A constant will give you a constant. So you can specify the shapes. You can also create tensors using some distribution functions. So we have normal here, uniform, or Poisson distributions. These are the parameters you need to assign for every distributions. And you can do this. This is how it looks like. So we have zeros, ones. These are constant, all 8 with 6 times 4 dimension, and normal, uniform, Poisson. And also, okay, this is, they are convertible, right? If you have a NumPy array, you can convert it to tensor by using TF constant. So this array will be converted to be tensor. Or if you have a tensor, you can convert back to NumPy. So they are interchangeable. So we just quickly covered NumPy. We just quickly covered tensors. Next is variables. So instead of tf.constant, we can name it. The function name is variable. So you can have two. They kind of be the same, but one is mutable, one is immutable. If you do this, you can see one is TF variable, one is TF tensor. And for TF tensors, TF variables, you can assign the elements, which means you can change the elements. So assuming now we have 10, 7, if you do this, your variable will have 5, 7. Okay, so that's why it's immutable. It's mutable. But if you do this for constant tensors, then you will fail. So there are also other useful things about tensor you can practice on your own, like indexing, slicing, and reshaping. Also math operations, aggregations. You can add them together. You can do elements-wise math operations, or matrix multiplication. So this is a matrix multiplication. There are 2 ways we can do this: absolute values or the power of A to B. So they are all similar to NumPy. If you're familiar with NumPy, there's no learning curve here. So these are the examples of sliding, indexing, and reshaping, which you can practice on your own. They are not very difficult. This is again math operations. So, okay. Oh, you can name the variables. So it has a name. Okay, so now let's cover something about automatic differentiations and the regressions in TensorFlow. So here we do not use a high-level API, this Keras thing. So everything we build from from scratch. So you kind of have a better feeling of how this the tensor calculations is conducted in TensorFlow. So the first thing we're going to introduce is called the gradient tapes. The gradient tapes, it's an API for automatic differentiations. It's computing the gradient of a computation with respect to some inputs. Usually it's TF variables. The TensorFlow records the relevance operations executed inside the context of a TF gradient tape. So the TensorFlow then use the tape to compute the gradient of a recorded computation, use reverse mode differentiations. So yeah, it's hard to understand, but I give you some examples here. We create a TF variables with initial values 5. If you do this context manager, it's like we're shooting record, we're shooting a movie, right? Yeah, we try to, so this is really a forward calculation, right? Giving X, we do a square to get Y. So forward calculation, we're recording the calculation like a movie. And that's why we call it tape. And once the forward calculation is recorded, you can calculate the backward differentiations. So if you're interested in dy over dx, then you just do the tape. Tape is the thing we just recorded, the forward calculation, and using the gradient methods of y over x, and you can print out the results. So this is very interactive. You get what you see. So if the initial value is 5, if this is square root of x, and so the differentiation is 2 times x and 2 times 5 equal to 10. So that's very intuitive. So also this gradient tape thing mostly only working for TF variables, because the thing you want to update in a neural network, mostly they are, not mostly, always, they always are TF variables. This weights and bias, they are all defined in TF variables. But sometimes if you want to work on the differentiations of a constant, then you can use this method called watch. So if x is a constant and you want to watch x, and you can also do the gradient as well. So very similar to what variables has. You can also work on a list of inputs, right? Realistically, in neural networks, you have multiple inputs. So this is a demonstration how you can do multiple gradient, multiple differentiation calculations. So we have W and B. We want Y equal to be X times W plus B. And also Z is the square of Y. And then you can see you can do the gradient of Z over W and B. And print them out. So this will not work. So let's run it. So now if you reassign a different value to W and do this, you will see the gradient is the same before you change the W. So W initially is 1, and you get dz over dw is 17. But if you change it to a different value, it's still this value. So that's because when you do this context manager, once it's done, it will record what it is done when it is done. So even you change a value afterwards, the gradient calculation has already been finished. It will not be updated. And similarly, you can also do computation gradient to some intermediate results. So not necessarily, yeah, you can do dz over dy. And here's also an example of how you can do this second order derivatives. So this is the equation of this is accelerators, velocity, and its distance. If you have a it's like a looped context manager, then you can see you can do the gradient of speed over time. All right, so once we know how to do automatic differentiations, I can show you an example of regression using this method without calling CAII. So here we create data. This is data we see before. It's just the y equal 2 times x plus some noise, and we plot it here. And now we define our weights and bias as variables with some initial value just randomly generated. This is our inputs and outputs. This is our like trainable data and labels. So we give some. Here we're going to use gradient descent methods to do the regression. So we run 10,000 approaches, and we do the gradient tapsing we just mentioned. And this is the model y equal to w times x plus b. And we define our loss to be the mean squared error. So this is like what people usually do in NumPy. Very similar here. So this is a mean squared loss, mean square error for loss. And then we do the gradient. So you get the loss over 2 hyperparameters, w and b, and you updating the parameters. So this is a gradient descent part, right? So this is your learning rates times the gradient, and you're updating w by subtraction this to have a new w and b, and you do it 10,000 times. And let's get it wrong. This is just some print. I think. Okay, I may have to run this first. Then run this. All right, so it is training. It is updating for us. Let's see some questions here. Okay. Okay, yeah, go ahead. Are we on time now? Yeah, we roughly have 8 minutes left. I finish this session and then take questions. All right, so, and you can, this is a plot of our regression, and you see it's doing pretty well. So here we're not using any sequential model in CAII. We are doing it by ourselves, and it provides you a lot of flexibility, which I'm gonna show you next tutorial, but it seems to be running out of time. So I can quickly run through the following two, especially the last one. So you know, sometimes so you have an understanding of why I talk this. All right, so the last tutorial is about different methods of you defining your neural network architectures. So we can skip the first one and quickly go through the second one. So the second part of the 8th tutorial, it's different ways of how you can build your models. So there are actually 3 ways how you can build models. In our first several tutorials, I use Keras sequential to build. Again, this is very elegant, very intuitive, right? So you just want to like sequentially building your layers, so input layers. Then you do ReLU for activation. So this is very intuitive. And there are 2 ways of doing this. You can have a list and then as arguments for this sequential model, or you can using the .add. You initial a model and then you keep adding different layers. So this is very intuitive. You can, most of the case, people like to use this. But occasionally, you have some difficulties, and because like what the name indicates, the model has to be sequential, meaning it has to be 1 layer after the other layer. So layer has a 1 layer ahead and 1 layer after. So what if you do something very innovative? What if you want to say you want to have 2 parallel branches, right? You want to branch 1, then branch 2, then forward a few, and then concatenating them together, and then split it to 2 branch again. Yeah, you can be as innovative as possible. In this case, Keras sequential cannot help. So there are more flexible ways of doing this. If you you may have seen this before, there are so-called functional APIs for you to build your models. So the way, this is like the syntax, how you can use this method. So you also calling Keras APIs to build layers. But after, at the end of each calling, you are given what you just you're using this as the last layer you have created, and you keep doing this to have outputs. So you have inputs and you have outputs, and then you call this Keras model to with inputs and outputs, and that's how you create this model. So we have examples of how you can do very innovative architectures. So the topology of your neural networks will be, instead of sequential, it can be really complicated. Yeah, I think we kind of running out of time, but the tutorials are available from GitHub. You are welcome to run it and test it and play around and get yourself familiar with this. We may be able to cover this in more details in our later workshop. But we still have 2-3 minutes to take questions. If not, I will stop here. All right, thank you.
Well, sure. Thank you very much for your tutorial. That was a very good tutorial, and very good notebooks to pick up and follow.
Yeah,
that's great.
Thanks.
Okay, so we are done for today, and thank you for coming. And this tutorial was recorded. It will be placed online shortly. So I'll see you next week. Our next tutorial will be on PyTorch. All right, bye.
Bye.